Okay, so we've just watched this video on the Wasson selection test. Some folks are wondering, why is it that the solution, the most efficient solution to this, is to turn over the 8 and to turn over the green card, and we don't have to turn over anything else? James, you were curious about this. Do you get the 8, why we should turn over the 8? The 8 part makes sense, yeah? Yeah, okay. This is most people. Most folks can figure out that if you flip the 8, you've got an interesting test. A test that can be failed. Because if I flip over that 8 and it's green on the other side, then we know that the statement that we're trying to test is false. If there are no conditions under which, like I flip the card over and it's like it's blue, it's green, it's got a pig on it, it's like got an even number, an odd number, like whatever, and it doesn't conflict with my statement, it's not a test that's going to give me any information, right? It's not going to be able to prove one way or another whether that statement is true or false. So the 8 will do it. The 5 doesn't give us anything interesting. Where a lot of people get stuck is, which of the two colored ones will yield anything, if any of them, right? If a card shows an even number on its face, then its opposite face is blue. A card that's blue, if I flip it over and it's got an even number, would my statement fail the test? If I flip the blue card over and it's an odd number, does my statement fail the test? No. And this is where some of the folks who are unsure are kind of like, oh, maybe though. And I suspect that you're thinking that if I flip over the blue one and it's odd, this might invalidate my statement, is because you think that if it's blue, then it's got to have an even number on the other side. But notice that the statement doesn't say that. The statement says if it's got an even number on one side, then the other side is blue. That's backwards, right? And one of the things that we need to recognize in this is that an if-then statement has a directionality that you can't just arbitrarily reverse, right? Not only does it have a directionality that you can't arbitrarily reverse, but there is a clever way of reversing it. But it's kind of weird. It's the second step. It's the step by which we would turn over the green card and figure out that this could be a test for us. If I flip over the green card and I find an odd number, that's consistent with my statement, doesn't disprove it. If I flip over the green card and I get an even number, I thought that if it was even on one face, then the opposite face was blue. How could it be even on the back and green on the front, right? Does that make sense? So a green one, if I flipped it over and it was even, would invalidate the statement. It's a good test. I should flip the green one as well. Folks have trouble with this one. This one's easier. This one's harder. And that kind of introduces 2 of the valid argument forms that we're going to look at today. One of them is called Modus Ponens. The other one's called Modus Tollens. We're going to look at 2 more, one called Hypothetical Syllogism and one called Disjunctive Syllogism. Before we get into these 2, we're going to take a little bit of a detour. After we're done talking about Modus Ponens and Modus Tollens for a little while, we're going to talk about necessary and sufficient conditions and then kind of pick back up. All right. So Modus Ponens is any argument of this form. If x, then y, x, therefore y. Remember I think it was in our last meeting, I was saying that deductive arguments or deductively valid arguments are valid just because of their form. I don't even have to look at their content. Do we remember that? It was 2 whole days ago. That even if the content is nonsense, right? Like if it rains, then I'm a bologna sandwich. Oh my God, it rained, therefore I'm a bologna sandwich. That argument is valid. The content doesn't matter, only the form. And notice that argument that I just gave, if it rains, then I'm a bologna sandwich. It did rain, therefore I'm a bologna sandwich. That's Modus Ponens. And it's pretty much just operating according to the definition of what this if-then statement is trying to say. The if-then statement says, if x happens, then y will happen. And if that's true, and if x happens, then y is going to happen. The only way that y could be false is if at least one of my premises is false. It would have to be false that if x, then y. It would have to be false that x is the case. Might try it out like something like this. If it rains, then I'll bring my umbrella. It rains, therefore, I'm going to bring my umbrella. If those first 2 statements are true, if my premises are true, the conclusion has to be true, necessarily is true, and that's validity, right? Yeah, this is a valid deductive form. Any argument that takes this form, that I can just I can figure out that like, yeah, there's a whole bunch of other stuff going on in there, but really at the end of the day, we're saying if this thing, then some other thing, this thing obtains, therefore the other thing must obtain. Any argument that takes that form is always going to be valid. And it's a common enough form that it gets a special name, a Latin name, in fact, Modus Ponens, which is short for an even longer Latin name, Modus Ponendo Ponens, which means, in Latin, the method of putting by putting. And the reason why we call it the method of putting by putting is I start off with this is sometimes called a conditional statement. Sometimes we'll call it a hypothetical statement, because we're not saying that x is the case. We're saying if x were the case, then y would be the case. I start with a hypothetical statement. I put forward x, and that allows me to put forward y. Right? The method of putting by putting. I'm able to put forward y and say, yes, y is the case, because I was able to put forward x and say that x was the case. Cool? Makes sense? This is the easy one. This is the flip over the 8 card in the Wasson selection test. It's possible to mess this up. A little bit rare because this form is kind of easy and intuitive for a lot of folks. It's possible to say something like, if that thing is a dog, then it's a mammal. That thing is a dog, therefore it's a mammal. I'm sorry, that's one that does work. It's easy to mess it up. For example, if I said, if that thing is a dog, then it's a mammal, and then I'm tempted to say, therefore it's a dog. But that doesn't work because it confuses my first premise. My first premise says, if it's a dog, then it's a mammal, and I seem to be operating under the belief that that also means that if it's a mammal, then it's a dog, but if-then statements aren't reversible like that. Cool? All right. Here's the harder one. This is the flip over the green card move in the Wasson selection test. And it's called modus tollens, which is a fancy Latin name. That's short for another longer fancy Latin name, modus tollendo tollens. Anybody want to guess what that means? The modus is the method. Method of taking, yeah. Yeah, good. The method of taking by taking. We start off with a conditional statement, or sometimes we might call it a hypothetical statement. If x, then y. And then we say no to y. Notice we're not saying yes. Modus ponens said yes to the second premise. It was if x, then y. And then what was the second premise in modus ponens? X. Yeah, we said yes to x in modus ponens. Now we're saying no to y. What's known as the consequent of this conditional statement. The first part is usually called the antecedent. The second part is called the consequent. So we say no to the consequent, and that allows us to draw a conclusion that we say no to the antecedent as well. This is modus tollendo tollens. It is valid every time. It's a little more complicated than modus ponens, and so sometimes folks get tripped up on it. And they don't recognize that, like, this is a valid move. This is always going to be an argument where if the premises are true, the conclusion is going to have to be true. So here's an example. That is, if that is a dog, then it's a mammal. It's not a mammal. Can I validly conclude that therefore it's not a dog? Yeah, because I said if it was a dog, it was a mammal. And it's not a mammal, so it can't be a dog. If it was not a mammal, but it was still a dog, then I'll have run afoul of if it's a dog, then it's a mammal, right? The only way for this thing to be a mammal, but not be a... Sorry, the only way for it to be not a mammal, but still a dog, is if this first premise is false. As long as those two premises are true, the conclusion has to be true, and that's validity. Modus tollens argument is going to be valid every time. It's not necessarily going to be sound every time, but it's going to be valid every time. This is still if it's valid, then it's deductively valid. Validity applies to deductive arguments. Yeah. In fact, today, the whole time, we're going to talk about deductive arguments. Yes? This one's a little weirder, right? Yeah. Should we do more? Yeah, do more examples? All right. Let's look at it a little bit busted. Kind of like we looked at one in the last one where it worked, and then we kind of like moved some things around and said like, oh, it doesn't work now. If that is a dog, then it's a mammal. That is not a dog. Does anybody feel somewhat tempted to say, therefore it's not a mammal? That would be wrong, of course, right? It's entirely possible to have non-dog, but yes, mammal, like me or a bear, right? So if that's a dog, then it's a mammal. That's not a dog, therefore it's not a mammal is what I want to do, but I thought modus tollens is always valid. Is that modus tollens?
If not X, not if not Y.
Yeah, this one says if X then Y, and then it says not X. But remember, modus tollens was if X then Y, not Y, therefore not X. It works if we do it in that order. It is like math. It's math with language. Many, many very smart logicians throughout the early 20th century attempted to prove, and with varying degrees of success, that mathematics and logic are basically the same thing. It's just in one case, we're talking about just the quantity of the things that we're talking about. In another case, we're talking about some other stuff. Like the truth values. It's a mathematics of truth value. So, more examples, perhaps. Yeah? More examples? Yeah, okay. Let's do another taxonomical one just to make sure. If something is a reptile, then it's cold-blooded. Show me a modus tollens argument that begins with that premise. If something is a reptile, then it is cold-blooded. My next premise should be, this thing is not cold-blooded, therefore it can't possibly be a reptile. Right? That would be modus tollens. If I was going to mess it up, if I was going to do a busted modus tollens, a fallacy, actually, a formal fallacy that's known as denying the antecedent, because I'm going to say no to the antecedent rather than saying no to the consequent, I would say something like, if something is a reptile, then it's cold-blooded. It's not a reptile, therefore it's not cold-blooded. Not false, invalid. Invalid, right? Yeah, the conclusion would end up being false, even if both of the premises were true, because you could be a fish and not be a reptile but still be cold-blooded, right? All right. Let's try one more. If it's raining outside, then I'll bring my umbrella. I didn't bring my umbrella, therefore it must not have been raining outside. And some of you might think to yourself, maybe you brought your umbrella, but a big kid on the bus stole it from you. And we're just like, oh, well, what does it mean to bring my umbrella? I brought it, but then it got taken from me. Or what if you say, what if you forgot your umbrella? What if it rained, but you forgot your umbrella? Then it would have rained, but you didn't bring your umbrella. Or you didn't bring your umbrella, but still it might have rained. But in both of those cases, we would say that my first premise, if it rains, then I will bring my umbrella, would have to be false, right? If that statement is true, then every time it rains, I brings the umbrella. Like I got a go-go gadget umbrella. And that would be one way that it, like, whenever it rains, I bring my umbrella. If I just have my umbrella all the time, then whenever it rains, I'll bring my umbrella. It would still be true. Do we see how this works? Let's explore this concept just a little bit more, because I think we can take another approach to it. We saw that Wasson selection test, which is one way at this idea of the difference between modus ponens and modus tollens, and how they're both valid. Here's another way of approaching it. We can talk about necessary and sufficient conditions. So all that I mean when I say that something is a necessary condition for something else is that the something else thing can't happen unless the first thing does, right? Let's use some variables. If A is a necessary condition for B, then B can't happen without A. Does that make sense? Is that pretty much the same way that you mean necessary when you say that something is necessary? Or like what a necessary condition would mean? A is a necessary condition for B if B can't happen without A. So let's consider these two concepts, male and bachelor, or being male and being a bachelor. They seem to have some sort of relationship with one another. What is that relationship? Can you be a bachelor without being male? Some of you might think, what if you're a female bachelor? We got a word for that. That's a bachelorette. If you're a bachelor, does that mean that you're male? So it's not possible to be a bachelor without being male. That makes being male a necessary condition for being a bachelor. And it also means that we can express this in a very familiar sort of a phrase, like an if-then statement like we saw before. If somebody is a bachelor, then they have to be male. I could also say it this way. If I wanted to say, instead of an if-then, I wanted to talk about like all, some, or none type statements, I could say all bachelors are male. Or I could do it symbolically, kind of like our argument mapping, and be like, ooh, bachelor, arrow, male. Or I could do it in this cool little Venn diagram over here, where I have, here are all the males. Some of them are married, some of them are unmarried. The unmarried ones are in this circle, we call them bachelors. And notice, all of the bachelors are inside of the male circle, which means that if you're a bachelor, you have to be a male. And that makes maleness a necessary condition for being a bachelor. Cool? Let's flip that over and talk about sufficient conditions. A is a sufficient condition for B if knowing that something is an A automatically tells you that it's a B. We would say being an A is sufficient for being a B. Every time you're an A, whoop, you're a B as well. That would mean A-ness. That's an unfortunate word. A-ness is sufficient for B-ness. I won't even talk about P and Q. All right. So being a bachelor is a sufficient condition for being unmarried, which is to say if I know that somebody's a bachelor, I automatically know that they're unmarried as well. I can say if somebody's a bachelor, then they are unmarried. And that tells me, knowing that they're a bachelor automatically tells me that they're unmarried. I could say all bachelors are unmarried, which tells me that if I know that somebody's a bachelor, because all bachelors are unmarried, I automatically know that they're unmarried as well. I could do it again. Bachelor, arrow, unmarried. I could do it again with the Venn diagram and put all the bachelors inside here and all the unmarried people inside here and say that if you're a bachelor, then I automatically also know that you're unmarried. Does anybody confused because it seems like I just did the same thing twice, but I called it different things? Joshua? Yeah? Okay. Anybody catch the subtle difference between the two? What is it? Sure.
It says that wheels are blank, a blank condition for fully operational.
So wheels are a blank condition for having a functioning bicycle, or a fully operational bicycle? Okay, yeah, from the worksheet.
You have to have wheels, but that's not all you need, so it's necessary.
So necessity is not the same thing as sufficiency. And we can see in this example with wheels and a fully functioning bicycle is that I need wheels for a fully functioning bicycle. But having wheels doesn't automatically mean fully functioning bicycle. On the other hand, fully functioning bicycle would automatically mean wheels, right? Because you've got to have wheels to have a fully functioning bicycle. I got the bicycle, so I must then have the wheels. The subtle difference in between necessity and sufficiency can kind of get obscured because they're sort of opposite sides of the same coin. It's the same relationship, but one's running forwards and the other one is running backwards. So notice this. If one is a bachelor, then one is male. Tell me, if you're a bachelor, does that automatically make you male? Yes. Do you have to be a bachelor in order to be male? No. So bachelor is sufficient for male, but it's not necessary for male. Let's run it the other way. If you're a male, does that automatically mean you're a bachelor? No, you could be a married male. If you're a male, is that necessary for being a bachelor?
Yes.
Yes. So necessity and sufficiency kind of like, if you have a necessity relationship one way, you're going to have a sufficiency relationship running the other way. And we can see this. Bachelor is sufficient for male, and male is necessary for bachelor. And this works every time. If I say if bachelor, then male, then it's sufficient this way and necessary the other way. And this is why, because we have this necessity and sufficiency being kind of opposite sides of one another, this is what makes the modus ponens, modus tollens thing tick, right? Is that I can run a valid argument from that if-then statement backwards, but I can't do it exactly the same way. One direction is going to be concerned with necessity, which says if I don't have this other thing, I can't have this first thing. And that's modus tollens. That's the one that takes away, that says if you don't have this, you can't take this. And that deals with necessity. And sufficiency running the other way is how modus ponens works. If I get X, then I automatically get Y, because we said if X, then Y. Does that make sense? A little bit? You might want to take a little bit of time in your thinking place to chew on this. But if you are the sort of person that would just trust your professor, I would say something like, trust me, they both work every single time. And if you're the sort of person that has trouble thinking through modus ponens and modus tollens every time, a very easy way to shortcut and save yourself the hard work of trying to make your stupid human brain, not your particular stupid, we all have stupid human brains, by the way. We can do things on paper that we can't do in our heads, right? So why make yourself think through it when you could just memorize the form? And every time you see if x then y, x therefore y, you're like, boom, modus ponens, my old friend, modus ponens, always valid. And every time you see if x then y, not y, therefore not x, you're like, boom, modus tollens, how you doing? That's always valid too. And anytime you see somebody say if x then y, not x, therefore not y, you'll go, that's not one of my friends. It's subtle, but it's tricky. What if we get both necessary and sufficient conditions? Ooh. This is a possibility. Instead of talking about unmarried and bachelor, or talking about male and bachelor, what if I consider the relationship between unmarried and male together, all of the things that are both unmarried and male, and that relationship to bachelor? If somebody's a bachelor, are they automatically an unmarried male? If I said, Adam's a bachelor, you'd be like, that means he's an unmarried male. And somebody would, maybe not. And you'd be like, we said he's a bachelor. Bachelors are unmarried males. We might say unmarried male humans. If you're an unmarried male, does that automatically make you a bachelor? So if you're a bachelor, you're an unmarried male. And if you're an unmarried male, you're a bachelor. This does go both ways. We can say, if you're an unmarried male, you're a bachelor. And if you're a bachelor, you're an unmarried male. One way that we might say this is we might combine the two statements. We might just say, if you're a bachelor, you're an unmarried male, and if you're an unmarried male, you're a bachelor. Another way we could say it is if and only if. Somebody is a bachelor if and only if they are male. This is another way of signifying it going both ways. I could say all and only unmarried bachelors are male. Sorry, all and only unmarried males are bachelors. And the way that I would represent this in my Venn diagram is I have all the unmarried people, all the male people, and where they intersect, those are the bachelors. And that would give us both necessary and sufficient conditions for being a bachelor. And something interesting happens when I've given necessary and sufficient conditions. And that interesting thing is, it turns out that I have precisely defined a term whenever I give both its necessary and sufficient conditions. I'm not going to spend a whole lot of time talking about definitions, but this is one thing to keep in mind. That if you're ever, and this is kind of crucial, very basic sort of rule for arguing clearly, is that you should be clear about what your words mean. If you're not clear on what your words mean, we run into all sorts of trouble. And I will have precisely defined a concept if I can give both its necessary and sufficient conditions. For example, if I say unmarried male, that is a precise definition of a bachelor. Unmarried and male includes all the bachelors. I don't miss any bachelors when I cast a net with unmarried male. And I don't catch anything that's not an unmarried male. Sorry, that's not a bachelor when I cast the unmarried male net. Does that make sense? I get all and only the bachelors when I cast the unmarried male net. And this is a good definition. Take, for example, and here's, let's try something that is likely not to be a necessary and sufficient condition for a definition. Can somebody try to define a dog for me? If I walked in here, it's like I just got hit on the head. My wife told me that I'm supposed to go find a dog, but I forgot what a dog is. Can somebody help me? What's a dog? Four-legged creature. A dog is a four-legged creature. Four-legged creature. Is that a necessary condition for a dog? Ever seen a three-legged dog? They exist. If you chopped a dog's leg off, would it stop being a dog? Yeah. Is four-legged creature sufficient for being a dog? What about a cat? A cat is a four-legged creature, right? But not a dog? So being a four-legged creature is not sufficient for being a dog. I don't automatically know that I'm a dog just by knowing that I'm a four-legged creature. Because I could be a cat, or a brontosaurus, or a horse, or a cow. I can go on. I know all sorts of four-legged creatures that aren't dogs. So yeah, four-legged animal is neither necessary nor sufficient for being a dog. Anybody want to try again? Four-legged animal that barks? Four-legged animal that barks? We have the four-legged problem still. It's a mammal that barks? I believe squirrels bark. Do you have to be a mammal that barks in order to be a dog? You have to be a mammal in order to be a dog. Do you have to be a mammal that barks? There's a process that people do to dogs sometimes called debarking.
You do that to trees.
That's a different kind of barking. Debarking is a surgery on their vocal cords that prevents them from being able to bark anymore. But I would warrant that they're still dogs. Although maybe you do that to a dog, they're just kind of like, I don't feel like a dog anymore. The same way if I got the dog fixed, the dog might say, like, I don't feel like a male dog anymore. That's right, there are some dogs that don't bark. There are squirrels that bark. There are humans that bark. Carnival barkers bark, yeah. Maybe that's a different sense of bark, but okay, fair enough. The mammal part seems necessary for dog, but it's hard to get both necessary and sufficient conditions. Perhaps if you were a zoologist, you might be like, I've got it, actually. I've got, like, it's a mammal that has exactly these properties. Yes? Domesticated carnivorous pack animal. Domesticated carnivorous pack animal. Cats aren't pack animals. If it's not domesticated, we might take a stand and say, like, if it's not domesticated, not a dog. It's a wolf or a dingo or a fox or a coyote, right? Okay, I'm liking it so far. Domesticated pack animal, mammal, right? A domesticated pack mammal. Carnivorous. Because you could have, like, pet pigs maybe, and those are pack animals, but they're not carnivorous. We might have it. We might have all and only the dogs until somebody brings in, oh, I don't know. Are sugar gliders pack animals? Chickens are kind of pack animals and they're carnivorous, but they're not mammals. Ooh, you might have it there. You might have us. All right. That would be impressive if it were true. What's that? A rat? Is it a pack? Yeah, rats are social. They're carnivorous. They've been domesticated, the pet rats have, and they're mammals. Ho-ho! Boom! There goes our definition. Why am I so excited about that? Now I don't know what a dog is. I'll go to the pet store and pick up a rat. My wife will be like, what's this shit? Dog? I don't know. All right. So necessary and sufficient conditions are important for defining our terms very precisely. And this also, we see, it ties to our modus ponens, modus tollens business as well. Here are two more common argument forms, common enough that they get special names. This one's called hypothetical syllogism, and we can see it's kind of a play on the modus ponens idea. We start with if x then y, and notice the next move. It's if y then z. And what I do in my conclusion is I just kind of eliminate that middleman y. Y acts as a link between x and z, and I say, like, if x then y, and if y then z, let's just do that a little faster. Skip over y altogether and say if x then z. And that works every time. For example, if Jack fails the exam, then he won't graduate. And if he doesn't graduate, then he'll have to stay for an additional semester. Yeesh! Therefore, if Jack fails the exam, then he will have to stay for an additional semester. And that works, right? That's valid. If those premises are true, the conclusion has to be true. And people do mess it up, by the way. And the way that they mess it up is they'll do something like if x then y, if z then y, and then they'll say if x then z. They won't have the y at the end of the first premise and at the beginning of the second premise. They'll have the y at the end of both, or they'll have the y at the beginning of both. And it won't function that way. Want an example of that busted version? If you study hard, you'll get a good grade. If you're exceptionally intelligent, just naturally, you'll get a good grade. Therefore, if you study hard, you're naturally exceptionally intelligent. It doesn't really quite work, though, right? Yeah. It's got to be if x then y, if y then z, therefore if x then z. And that's called the hypothetical syllogism. Here's our last one, which will give us all of 5 minutes to work on the worksheet together. X or y is my first premise. That's a new one. I've been talking about if-then statements. Now I have an x or y statement. X or Y, not X, therefore Y. This is what's known as a disjunctive syllogism, and this works every time. This is always valid. Not necessarily sound, but if those premises, if like my first two premises, whatever I fill in X and Y with, if those are true, then that conclusion will have to be true. For example, Dr. Rosenfeld teaches at A&T or UNCG. Rosenfeld does not teach at A&T, therefore it must be the case that he teaches at UNCG. That first statement, that A or B, or that X or Y statement, just says it's got to be one of the, at least one of these two, right? It's either this or it's this, and the second premise just takes one away. And since it has to be this or this other one that's off the table now, this is all that's left. And that's how the disjunctive syllogism works. Beware with this one, because the word or is a little bit ambiguous. Sometimes we mean it one way, and sometimes we mean it another way. Sometimes folks are tempted to say, X or Y, X, therefore not Y. And sometimes that works and sometimes it doesn't. And it depends on how we mean or. The names for these two different senses of talking about or are an inclusive or an exclusive sense of or. An inclusive sense means when I say A or B, or X or Y, it could be X, it could be Y, or it could be both. Right? It's got to be at least one, and it could be both. That's an inclusive sense of or. And we call it inclusive because it includes the sense that, like, yeah, it could be both. An exclusive sense says this one or this one, but not both. Make sense? So if you're ordering breakfast at a diner and the server says you can have grits or home fries, and you say, is that an inclusive or an exclusive or? You'll have sparked a really interesting conversation with your server about logic, and they'll thank you for it. They'll be like, finally, somebody who wants clarity in their order. It's inclusive, actually, and you go, well, then why not both? Let's get grits and home fries, because that's grits or home fries as well, right? All right. These are the four valid forms that we're kind of introducing now. We're going to stop talking about validity for a little while after this. At our next meeting, I'll talk a little bit about what are called formal fallacies that have to do with busted valid arguments. But after that, we're going to leave deduction alone until after spring break, and we're going to focus on inductive arguments. But we get a sense of how this works? If I gave you an example of an argument, you'd be able to tell me it's this one, this one, this one, or none of them. It doesn't match any of those. And if I gave you some questions about, that were something like, if you're an eagle, then that is a blank condition for being a bird. You'd be able to answer that question? You've got the worksheet. This is some practice on that. I'll post the solutions. You'll also have a homework assignment that's posted. And at our next meeting on Friday, we'll talk about fallacies. I'll post the Section 1 quiz, and I'll start talking to you about our first exam. Yes? Mm-hmm.